Okay, I have just set aside the mic. I'm not going to use that. If those of you in the back have any trouble hearing me at some point, please let me know, shout out or something. Okay, and I'll just talk louder. All right. Okay. Let's see. All right. All right, so what we're going to do now is we're going to start moving into issues directly of divide and recombine. I've given you some background, so we're going to start talking about division methods and some ideas about this. And then what I plan to do is then we're going to start looking at the voice over IP data, and we'll talk about everything else in the context of that data. But before I do that, so that you can really understand what were the idea, what were we trying to do, why were we analyzing the data, what were we attempting to accomplish. I'm going to have to tell you a little bit about voice over IP, but let me ask. The nice thing is, most of you are in computer science or electrical engineering, so you probably know about networks. So how many of you have taken a course in computer networking and feel as though you know a fair amount about it? Okay, that's good. All right, well, I will do some background, but I'll probably move quickly through it. So, all right. It occurs to me, though, that we do have actually an immediate answer of a question that came up yesterday, which was an interesting and very good question. So, Jeremiah, you want to answer? It turns out Jeremiah realized he actually knew the answer to the question at the time and understood it, but then had forgotten about the name of the system, I guess.
So the question was, what's the difference between Rippet and Ricardo? And the answer is, there's this notion of structured data and unstructured data. And while we're talking about principles by which we divide data up between subset variables and that sort of thing, we're still working essentially with unstructured data. And we're also, with Rippet, we're also trying to get the Mapreduce interface. So when you talk about how Purdue actually implements Mapreduce, it has literally a map interface that you implement and the reduce interface that you implement. And when we designed Rippet, we wanted to expose that interface as directly as possible, and that's what we succeed in doing. Ricardo is much more a package about putting our data on the HDFS in some sort of structured fashion. And I actually looked at it and I couldn't find the Mapreduce. So if there's good examples of that, I'd like to see them, or much lower level.
Okay, good. I think one of the things about Rippet to understand is that we're trying to preserve exactly the same programming environment as you have when you're not having to do large amounts of data. In other words, it looks, nothing is limited. It's completely general, what you are able to do. And so I think what the IBM folks have done is to make a more restricted domain by trying to specify certain rather specific kinds of analyses. Is that a fair statement?
Yeah, I really want to learn more about it, but it's different. I mean, it's a whole different idea.
Right.
And when you see actual examples of how we implement Mapreduce, it's so clearly Mapreduce and so clearly R that you'll get it. And if you've seen Ricardo before, you'll instantly probably understand it.
Okay. All right. Good. Okay. So we're going to start out with conditioning variable division. What's happening here? It is a fundamental division method of divide and recombine. Certain variables are selected as conditioning variables, and the data are divided up according to the values of those conditioning variables. Now, these are variables that are important to the analysis. So you're seeking to try to understand what their behavior is, as well as what's happening with the variables that are varying within subsets. So the conditioning variables, there are other variables that aren't a part of the conditioning that vary within the subsets, and they are within subset variables. And so, and then the conditioning variables become between subset variables because there's one value for each subset. And the idea is that you study the relationships of the within subset variables and how they change with the conditioning variables, the between subset variables. Now, the thing about conditioning variable division, though, is that it's a powerful analytic tool, period. It doesn't matter if you have small data. It doesn't matter if you have large data. So conditioning variable division arises as a best practice for data analysis, particularly when you are in the mode of trying to understand the patterns that are in the data. To be more specific, when you're trying to, say, build a model for the data, some probabilistic model for the data, or you're seeking to use some probabilistic model, and you'd like to know if, by the way, does it happen to fit the structure of the data? Now, because it's powerful for small data too, there's lots that's already going on in data analysis that uses conditioning variable division. For example, the display framework called trellis display is exactly about that. It's about breaking up the data into subsets, and then it's a mechanism by which you can display those subsets. And R has the lattice graphics package, which has implemented the trellis display framework, and this book by Depay and Sarkar on lattice graphics. So if you're an R user and you haven't already jumped into lattice graphics, I would encourage you to do it, whether your data are large or small. In terms of computation, there has always been, going all the way back to the beginning of the S language, a notion of apply functions, where just computationally you say, hey, I specify some variables. I say to you, take this data frame, say, or these data, these observations of a number of variables, and I want you, for these values of the conditioning variables, I want to break up the data, and I want to repeat the same computation. And I specify what that computation is. So computationally, what is that? That's actually and then you run the same code on all the subsets, and then you bring it back, and then you put it together. So what does that sound like? Doesn't that sound like Mapreduce? So wasn't Mapreduce in S in 1980? Well, yeah, it was. So that concept has been there for quite some time. So you might say, what we're doing is we're just taking an old concept and we're trying to extend it in part to large complex data sets. But we don't want to give it up. And as a matter of fact, this helps us with our computation. So it's a double win. So there are the apply functions, and more recently, Hadley Wickham has put together a really nice package for managing the data structures that arise when you do this kind of thing. Okay. So let's illustrate this. Let's say like we're back years ago, and we've got this data set, and we've got 120 observations. I'll use this to illustrate what I mean by what you actually do. So here's an example. So this is data from the 1930s. So I think probably this gets the prize for the oldest data set looked at in this summer school. But I'm not sure. Who knows? Anyway, 1930s. It's measurements of barley yield, 120 measurements of barley yield, and that's the response in an experiment at the Minnesota Agricultural Experiment Station. There are 6 sites where the barley was grown. There were 10 varieties of barley grown at each site, and the yield measured in each of 2 years. So 6 sites, 10 varieties of barley, 2 years. And so 6 times 10 times 2 is 120. And for each of the combinations of these 3 variables, you get a barley yield. The history of the data is that they were published in R.A. Fisher's landmark book, The Design of Experiments, because this represented the use of some of his ideas in their experiment. And through the decades, the data set became a canonical one that was used by a lot of people to illustrate new methods where that would be applicable to data of this sort. But as you're going to see, the use of trellis display in the 90s showed that it would appear that there's really an egregious error in the data. Okay, so what we're going to do is we're going to start looking at the data, and what we're going to do is we're going to select 2 conditioning variables, site and year. So we'll take all combinations of site and year. So there are 6 sites and there are 2 years. So that's 12 combinations of those 2 variables. And that's how we'll break up the data. So there's 12 subsets, but within the subset, you have 2 variables that are varying. You have variety and you have yield. And so there will be 10 values of pairs per subset. And here is a trellis display of this conditioning variable division. So what do we have here? I know those labels are probably a little on the smaller side, but anyway, I will tell you what's going on. You don't really need to know what the names are because they probably won't mean too much to you. But on each panel, we have a display where on the vertical axis we have the variety. So Trebby is at the top, Wisconsin number 38 is at the bottom, and Svansoda, is next, and then Svansoda is at the bottom. So 10 varieties, and on the horizontal axis we have barley yield. All right, so this panel shows the yields for the 10 varieties. Where? 1932, Grand Rapids. Now what's happening here is that as we go left to right, we're going through year. So this column is all 1932. This column is all 1931. And as we go through the rows, the site is changing. So we have 6 rows of panels, and that's site, 2 columns of panels, that's here. Okay? All right, so that's the conditioning. And here's a visual display that carries out the conditioning. So what we're doing is we're looking at the within subset variables, variety and yield, and we're seeing what the pattern is, and then we're comparing the patterns across divisions. Okay, now I'm going to come back to this. Okay, so this view graph is what I just said. So what we want to do is we want to see how the relationship of variety and yield changes with site and year. For example, we expect some sites will be better than others because the growing has got better conditions. And year matters because weather changes from one year to the next. So we want to know what's the relationship. Maybe what happens is that all that happens is you add a constant to the yields as you move around the whole display. It's just basically a constant. You know, it's that these things are just shifting around in a constant way. So you say, well, it's an additive effect, these variables. But maybe actually there's a tremendous interaction as we go from 32 at Waseca to 31 at Svansoda. You know, the yield values are reversed. You know, top goes to bottom, bottom goes to top, just because there's some interaction between site and the variety. But that doesn't appear to be happening, as you could see. Mostly, shall I say, they're varying together. Now, I have more to say about the display. And we'll come back to it. But let me just say that even with small data, what you find yourself doing is carrying out multiple conditionings. Because after all, you say, well, I mean, how come you decided to condition on site and year? I mean, why didn't, we're conditioning on site and year. Why didn't you condition on variety and year or variety and site? Well, the answer is, why not? Let's do it. So you find yourself doing many divisions and many conditionings as a way of understanding the behavior of the data. So typically, conditioning variable division is carried out. This is for small data sets and for large data sets, as you'll see. It's carried out a number of times with different conditioning variables. So multiple separate divisions. So for example, for the barley data, it's certainly informative to condition on variety and year and plot site against yield for each of the remaining 20 subsets. So here's a way of doing that with trellis display. We're actually going to have 2 pages. You can spread, when you make a trellis display, if you have a lot of panels, the way we're going to have, as you'll see shortly when we have a large amount of data, then you can send the panels across. I'll use the word pages. I mean, I know it sounds very like, a printer or something, print, but anyway, we just use that term, okay? So there actually are pages in a PostScript file. But by the way, you might say, oh, you're still using PostScript? How come? Well, it's faster. Okay? So that's the only reason. I mean, we're not stuck on PostScript, except when you put up something, especially when it has a lot of data in the display, it goes a lot faster than PDF, and we don't have to stand around here waiting while the display, draws all the points. So, okay. So, so what do we got here? We've got 2 pages. So we have now conditioned on year and we've conditioned on year and variety. So here's Svansoda, and here's Manchuri, Velvet, Glabron. Oh, the second column, we're still going. All right, and the reason why we can do that, and that we don't have to have, we can do this because we don't have labels for what these panels are in the margins. The labels go with the panels themselves. And I would just say we can't spend too much time on the design of trellis display, but that's one of the major features that gives you the flexibility. The labels travel with the panel, and that gives you tremendous flexibility in the way you lay things out. All right. Okay, so here's the first page, because this is all 1932, and this is 1931. Okay, so we go back and forth. Now, as a practical matter, of course, we don't have to make these different pages. I was just doing this to show you that there is this notion of pages. Okay. Now, let's go back to the trellis display of the first one I showed you. So remember, this one here. Okay, so we're variety against yield, conditional on site and year. There's something that's been done in the drawing of the display that is actually extremely important to perceiving the effects. And this is just a general principle of data display that you will find yourself wanting to invoke a lot. And that is that there is a specified ordering to the variety yields. So variety is a variable, it's categorical, and it's got 10 categories. We have ordered these by a certain mechanism, which I'll tell you in a moment. We have ordered the rows by that same mechanism and the years as well. And the mechanism is this. For each variable, each level of each variable, we take the median across all the data for that value. So you have Trebi, say, you have the site Wasika. So there are 20 measurements of yield at Wasika. So we take all 20, we take the median, we do the same thing for all 10 varieties, and we order by the medians of the variety categories, the 10 of them, we order on each panel by the medians. So when you go from bottom to top on a panel, What's happening is that this is ordered by the overall value of that variety variable in each case. The same thing with the sites. The sites are ordered from smallest overall to largest overall. And we've done the same thing with the years, although it's not so salient in this particular case. But I mean, either ordering would have been fine because there's only 2 of them. But it could matter if we had more than 2. Anyway, okay, so that's an important aspect of this display. Now, when you look at it, what's happening is, remember, as we go up through the panels, overall, the sites are increasing. So as we go up, the medians are increasing. So we go up here, and we see that, well, in each year separately, as we go from Grand Rapids to Duluth, we have an increase in the values in 32 and 31. And then the same thing in 32 and 31 for University Farm. And then suddenly, uh-oh, what happened here? Morris. The pattern's off. And then, but it continues on. As we go up now, they're still, in each year separately, increasing. They say, well, that's interesting. Now, of course, this is 1930s, so anything could happen. It could be easily happening. There was some very bad meteorological event that occurred at Morris. Happened all the time. However, there is something interesting about this. As you look at it, you say, you know what? Get this, you look at it carefully, you say, this sort of looks to me like if I interchange the years, it would fit the pattern. Now that's interesting. So just that little visual cue, I mean, suddenly a light bulb goes off on your head. All right? So that's a striking phenomenon. So this view graph just says that. Well, let's change them. Well, I'll be darned. Look at that. Change the years. And Morris now fits the pattern perfectly. I wonder. All right. Well, let's wonder for a bit. Okay? Let's just wonder about that. And we'll come back to it, because my purpose here is I don't want to spend too much time on barley data. I just wanted to give you an idea of conditioning variable division and its power. Okay, now, the one thing to keep in mind, though, is we've done the division, and this recombination is a visual recombination. So that's one of our 3 categories of recombination. It's visual. I make a picture, and I look at it, and I'm doing a visual reduce, or a visual merge, whatever word you want to use. Okay? But it's as valid as any numerical merge, and very, very powerful. Okay. Oops, I want to be here. Okay, let's get to the voice over IP data. All right, so what's happening? Traffic on the internet, traditional voice telephone traffic, the old bell system, with the ringtone, all that. It's migrating to the internet, where it's referred to as voice over the internet protocol, VoIP, VoIP, I guess. And we still use the term voice, even though, it sort of harkens back to the old telephone network where there was only voice. But in point of fact, there are, even on the current old telephone network, which is still out there in part, there's things other than voice. There's fax, there's point of service transactions like credit cards and things like that. So, but we still use the word voice. It's just, and that's the name. So it's voice over internet protocol. But there's more than voice. Now, each voice over IP call has 2 directions. People are talking, or machines are communicating. So there are 2 semicalls, we call them. Now I'm going to describe technology, but understand that while the overall idea of voice over IP is the same from one implementation of voice over IP to another, there are configurable parameters in any implementation on the internet, and I'm going to describe voice over IP with the implementation of the service provider network from which we collected these data. Okay, so I'll just talk about things like 20 milliseconds, for example, which is configurable. All right, so what happens? A voice signal comes into a source internet gateway that breaks that signal up into packets. So each packet contains 20 milliseconds of the signal. Now the signal takes up 1280 bits in each packet, and then to that you add a 320-bit header, which is for control of the connection, so that you can get it to its destination and then put it back together again when you get to the destination. So the total size is 1600 bits. This 1280 bits corresponds to 64 kilobit speech, which is a standard speech rate. And once the 20 milliseconds is accumulated for a packet, the source gateway sends it on its way for its trip across the internet. Now, that gateway transmits that first packet. I mean, it's been packetized, and then it puts it on an output link and sends it to a first internet router. And then, of course, the path across the internet consists of routers and links connecting them until finally you get to a last IP router, which then connects to another gateway, which transforms back to the signal, whatever it might be. And of course, there's varying things it can be at the ends, but it goes back out of IP technology. So we collected data, a large complex data set of voice over IP traffic from a link on the Global Crossing Network that connected a gateway in Newark, New Jersey to a first router, also in Newark, New Jersey. Probably in the same room, actually. Okay, so, and we collected packets in both directions for, each call has two directions. Any call that's using it in one direction, the other one is coming in the other direction. The other half of the call, the other semi-call, is coming in the other direction. So we got both directions of calls over a 48-hour period. So altogether there are 332,000 calls, and so therefore 664,000 semi-calls. So altogether there are 1.315 billion packets. Now for each call, the gateway is communicating with some other gateway, 26 gateways around the world. For example, London. They're spread all over the world, Buenos Aires, London, quite a few points in Europe. Okay, so for each call, the Newark gateway is communicating with, say, London. So there's a London to PSTN. By the way, this Newark gateway, for a variety of reasons, we just give it the name PSTN. That actually means Public Switch Telephone Network. That's the old name, but there was no good reason for that. We just, for some reason, started calling it that, and we've maintained it in our display. So I'll call that here. Okay, so London to PSTN has a semi-call whose packet source is London. And then London to PSTN has another semi-call whose packet source is the PSTN. Okay, so that's how we think about the direction on a link. There are two directions. One is coming out of the IP router to the gateway. The other is the gateway to the IP router. But we designate that by destination PSTN, source PSTN. Okay, any questions about this? Pretty easy so far, I think. Okay, well, here's a diagram just to make sure. So source PSTN, voice signal goes to the PSTN gateway, first IP router, across the cloud, last IP router, London gateway, back to voice signal, destination London. Okay, and the other way around. There's another thing happening here, which is silence suppression. Source gateways frequently do this, and in particular, Global Crossing was doing it, and still are. So the algorithm uses a signal strength to detect the beginning of an interval of silence. And it stops sending packets. So you do this obviously to sort of, decrease the amount of traffic that you have to send. And it keeps listening, and when it finally hears the signal strength get sufficiently large that it says, oh, this is probably the transmission really for real starting up again, it resumes packet transmission. So each semicall consists of alternating intervals of transmission of packets and silence. Okay? As you'll see, that's important to the story. Now, the path across the internet. So each router on the path across the internet has input links and it has output links. So comes in on an input link, the router reads it and figures out, okay, so you've got to go out this, this output link, looking at its tables. Now, all packets of a single semicall will typically use exactly the same path, in both directions. They tend to configure things in that way. Now, the output link at any given moment is carrying the packets of many voice over IP calls. And so you have call number 1, its packets are coming in. It's got arrival times of packets for transmission on the output link. And they're intermingled with packets from call number 2, say. So now the interesting thing is that statisticians would say the traffic, the arrival times on the link, on the output link, are a superposition of the arrival times of the individual semicalls, whereas the network engineers say that they are statistically multiplexed. Okay, so you would think it would be the opposite, but no. They use the word statistics, statisticians use the word superposition. So for our collected data, the timestamp of each packet is the arrival time on the output link of either the gateway or the router, and the traffic is multiplexed. All the packets of individual calls are intermingled. And that's the way the raw data come in. Now, for the raw data, the variables that we collect are the following. We look at every single packet and we timestamp it. So we know the arrival time. This is done in hardware. So the expectation is quite a lot of accuracy. So we have, that's number 5, packet arrival time on the link. And it's when the interface writes the first bit on the link. Then we look inside the packet, we get the source gateway IP address, the destination IP address, the port number of the source gateway, and the port number of the destination gateway. The arrival time, as I said, and then a 2-level categorical variable, which is, it's a flag on the packet that says, I am the beginning of a silence interval, or I am a packet that's carrying voice. That's how we know a silence interval has started up, for sure. Now, variables 1 to 4, these 4 numbers here are the same for packets of each semicall, and collectively, they uniquely identify the packet. So if I have that 4 tuple, then I know which call is which. Okay, and that, of course, for the transmission across the internet, that's the way, when it gets to where it's going, that's how the codec knows how to categorize these things, or how to bundle them back together again. Okay, so the semicall identifier, we can think of it as just simply being a concatenation of these 4 variables. Okay? And you might say, well, gee, wait, aren't they the same? Aren't they the same for the other direction of the call? Well, no, because the source and destination have been reversed for the other direction. And that's how you know. The numbers are all the same, except source and destination have been interchanged. So you know, hey, these are the packets for the other side of the call. So why do we do this? This is important to the story. First of all, our purpose was to develop a statistical model for the multiplexed arrival times of the packets as offered load to the network. Okay, so first of all, the purpose of this is network engineering. We are not trying to figure out, what's the interplay between, the two semicalls of a call. That has absolutely nothing to do with anything. Okay, so we really, in the end, there's a little bit of connection between the two, but in the analyses we carried out, because it's about network engineering, and they're on different links. They're not on the same link. So, the relationship of these two is not really so important, although there were a couple of things in the modeling where we did decide to cross over and say, all right, go find the other half of the call and we'll put them together. You'll see a little bit of that. But for the most part, this is traffic engineering. And that, in fact, is the idea of the modeling. We wanted to be able to develop a model that would generate multiplexed voice over IP traffic that was valid and really characterized the real behaviors out there when you look at a link, and use that for generation for network simulation, so that we can try different traffic rates and things of that sort and change some things, change the rates, change the link speeds, find out how much traffic you can put on a link and how can you configure voice over IP in order to optimize quality of service. Okay, so generation. And it's, of course, essential to reproduce statistical properties within and across semicalls. So we need to know something about what's the mix of the different well, let's say, different types of traffic. So we have to be able to reproduce that as well, to reproduce what it would be like on a real service provider's network. So statistical, shall we say, the statistical verisimilitude is utterly crucial. And that is certainly not just the opinion of a statistician who likes to do statistical modeling. That certainly reigns supreme in the field itself. You'd better reproduce these and demonstrate you're reproducing it if you want anybody to accept this as a model to be used in their simulations. Now, oh yes, one important thing here. This is the offered load. What we seek to model is the arrivals right out of the gateway to whatever interface is going to be sending it out. So they're coming in for transmission. That's what we're modeling, because you don't want to, you see, you want the sort of the pristine traffic coming in, and then the network simulator will take care of everything else between. Okay. Model architecture and simulation. You might say, oh, does a model have architecture? I don't know. It just popped in my head and I wrote it down. Why not? I mean, why shouldn't a model have an architecture? Everything else does. So let's see if we like that term. All right. So here's the way it works. First of all, there's a model for semicall arrival times. They're coming in at this rate per call. So we have a model for packet arrival times. Then you have a model that generates the packets of a random semicall. All right? So what do? Yeah, sorry.
What kind of model are you using? Well, what kind of model are you using for the arrival processes as well as the packet arrival times?
You mean of the individual semicalls?
Yeah.
Well, okay, let me answer the first one. Poisson.
Are you assuming IID or stationary?
Oh, no, they wouldn't be stationary. Oh, well, it depends on what time frame you're talking about. The network simulations that go on for quality of service, you're studying really relatively small intervals, because the queuing and all of the arrivals are going on like mad. So the queuing is fluctuating over relatively short time periods. So you don't simulate for a week. You simulate something that would that would be applicable to a relatively short period of time, a minute or two, and then you sort of you do the network design capacity planning based on peak loads. So when you do the simulation, you say, okay, I'm just going to simulate and find out what the queuing is like during a period of peak load, which is dictated by which changes with time of day and things like that. Okay. Yeah, Poisson. I mean, that's actually quite surprising. Now, I just want to say one thing. We actually got rid of a whole lot of little calls. This isn't part of it, but it's sort of interesting that if you look at any telephone network, you will find there are just an immense number of really small calls that, for one reason or another, don't make it. Somebody changes their mind about making the call, or the call has a little bit of trouble, or something like that, especially with international calling. So a very large number of extremely short calls, in the order of a second or so, those were eliminated. Those things were bursty. I mean, those things, in the network parlance and statistical parlance, they were sort of, had elements of long-range dependence in them. But but once we get rid of those little calls, guess what? It's Poisson. I mean, that's the way it was in the old telephone network, and now we're still back there with voice over IP. Okay, so that was nice. Now, the model itself for all right, how do you generate the packets? It's a model for sequences of, alternating sequences of silence and transmission is really the heart of the model. So it doesn't have a name. It has the voice over IP model in our paper. That's its name. I mean, it's not categorizable, like, oh, well, yeah, I use a hidden Markov model. We studied the data in tremendous detail, and on the fly, based on the patterns we saw, we developed a model and the stochastic specifications based on what we saw. Okay? Okay, so what do? We generate the arrival times, and we generate the packets of individual calls, and then we numerically multiplex them. So as part of your simulation, you numerically multiplex them like the router does when it's, well, I shouldn't say like the router does, because it's not like the router does, because there's queuing. We just put them together. We multiplex them. They're arrivals, okay? And then that goes into the queuing simulation. So the modeling is at the call level. We didn't try to model directly the multiplex traffic. You could do that. You could say, well, why don't you just model the multiplex traffic and then, look at how the model changes with the traffic rate. Well, that's actually a harder job in many ways. But also, this is more flexible because we can make changes that reflect different kinds of configurations in voice over IP. And we know how to do it per call, but you wouldn't know how to do it with the multiplex calls. Okay. Okay, now, there are a certain number of cases where the data have a very natural division. And this creates what what we call a basis division for much or all the analysis. So in other words, the data are embarrassingly divisible. And of course, we're using that term because it's a copy of the computational term to which it leads, which is embarrassingly parallel. Now, this is the case for semi-call analysis and modeling of the voice over IP data. We'll talk about that in a second. But I just want to say there really are a fairly significant number of embarrassingly divisible data analysis problems. And one really big one, if you think about it, is simulation. Provided each simulation, I mean, I'm assuming that you're not running, 3 simulations, each of which, involves, 10 terabytes of data. I'm talking about lots of things to get down statistics, for example. Like the bootstrap. How many people are familiar with the bootstrap? Okay, all right, beautiful. I mean, that is embarrassingly divisible because The data in that case are all the samples you draw in your simulation. And depending on the tasking, you can go a lot faster. So Bo Lee, who does spatial analyses here, had simulations, and it was taking her weeks to run the simulations, so she has joined us in our cluster, and our simulations went from weeks to a few hours, just because she's able to run those things. I mean, you might say, oh, well, that's too easy. Come on. No, I mean, that's not, you're cheating. Well, okay, we're going to take the easy things too. All right? Doesn't have to be hard to be, you say, well, can you do the hard ones? I don't know. We'll do the easy ones first, okay? So, okay, so anyway, semicall is, for our data, an obvious natural basis division. We will divide up the data by semicall. Yes?
So basically by embarrassingly divisible, you mean that you can partition your data appropriately, or do you mean that you can choose your conditioning variables for visualization?
Well, they're the same thing. I mean, you're going to pick something which is, of course, very, very cogent to the analysis. I mean, when I say embarrassing divisible, I mean, you got some variable there that is central to what you're doing. And of course, in this case, it's utterly central, because we're actually trying to model the packets in each individual semicall. All right, so there's this variable, and you break it up, and this is, it's easy to do, and it works. And I mean, obviously, this is a slightly soft meaning here of this, but I think we can all agree, whatever we might mean, this qualifies, because we have 1.5 billion packets, but we have 664,000 semicalls, and we'll just say, hey, each semicall is each semicall is a subset. The information, all the variables that we measure in a semicall, that's one subset. Yeah.
Specifically talking about bootstrap, for example, so you would bootstrap for each of these semicalls, or
You would what?
you would bootstrap your data conditioned on each of these semicalls. For example, if you had
We did that. We actually did do that. Yes, exactly. That's right. You're saying, if you got you're doing something with semicalls, and then you say, oh, hey, I've got this model. I've got some estimators that, tell me. Well, beside that, it was I just want to say, I'm not going to talk about the actual modeling. We're going to talk about a very important analysis that got done in jitter. So we won't get into the modeling. But yes, yeah, exactly. You could take each one and bootstrap. And we did do that. So that's like, except in that case, we did it in place. We didn't break the bootstrap up. So, I mean, we've already got, well, not this many, because we didn't do it with this many calls, because by the time we got to when we were doing the data, we had gotten rid of the little calls and things like that. So, okay, so in this case, the conditioning variable is the semicall identifier, formally. So you got all this packet level data, the raw data I showed you just a moment ago, what we're collecting right here. For each packet, okay, where am I? Right here, yeah. For each packet, those are the within subset variables. They're changing, they change as we go from one packet, from within a call, within a semicall, we have the arrival times, and we got all the packets and the measurements on them, and they're changing within semicall because there's a lot of packets, okay? So there's two within subset variables: the packet arrival time at the monitor and the flag that indicates whether or not a packet has voice content or is a silent start packet. Okay? All right, any more questions? All right, let's take a break. We'll see you back here at 3:30. Is that right? No. Yeah, 3:30.